So welcome everybody to the lecture on ultra-cold fermions, where we'll focus on some experimental basics. And we work a lot of ultra-cold fermions, so it's close to my own research field. We have experiments at both institutions, the experimental physics at the university and also the ICOCI Institute of the Austrian Academy of Sciences. And so let me start with the question for you. Why are fermions interesting? And I would say even more interesting than bosons, but this is a matter of taste. Why are fermions interesting? Somebody wants to try and answer?
Because you can also, if you understand fermions, you can also investigate bosons, because two fermions are then a boson.
Excellent answer. So that means if you put two fermions together and form a composite particle, it has an integer spin and is a boson, and this changes the physics. So in a way, you can say that fermion plus fermion is boson, so boson physics appears as a special case of fermion physics. So fermions are more general. Another reason, if you think about the constituents of matter, how matter is composed, nuclear matter, quark matter, the electrons, all these fundamental particles are fermions. Electrons in solid state systems, neutron, protons, quarks in hadronic matter. So if you want to learn something about the basics or how the basic constituents of matter interact and form new states of matter, then this is something for the fermions. And finally, the last point is kind of a word which appears quite often in the field. It's universality. So what is meant by universality? Universality is illustrated, with this table, for example. These are all different fermion systems. The Neutron Star is a dense fermion system. A white dwarf is a dense fermion system. For the Neutron Star, it's neutrons, and for the white dwarf, it's electrons. And the Fermi pressure stabilizes the Neutron Star and the white dwarf. Otherwise, they would collapse. In a metal, you have the electrons, fermions. And in our ultra-cold gas, we have, for example, in most experiments now worldwide, lithium-6 atoms. So if you look at the masses, here you have the one neutron, mass number 1, ultra-cold gas, 6 atomic mass units roughly, and the electrons here, 1/2000 times the atomic mass unit. And the number density in the neutron star is something like 10 to the 44 per cubic meter. Now it's get less for the white dwarf, gets even less for the metal, and for the ultra-cold gas, it's only 10 to the 18 per cubic meter, or 10 to the 12 cubic centimeter. So you see in the density, number density, there is a factor corresponding to how many? 26 orders of magnitudes. 26 orders of magnitudes. 26 is quite a lot. The Fermi energy ranges from 70 mega electron volt to, if you want to express it in electron volt, to 300 pico electron volt for the ultra-cold gas. Fermi temperatures are here in the range of 100 gigakelvin. In the ultra-cold gas, it's 3 microkelvin, or less even, 1 microkelvin in some experiments. You see there's an enormous range covered by these numbers, many, many orders of magnitudes. But universality means that the physics is one and the same. So if you compare, for example, a neutron star, so I don't know how a neutron star looks like. I found this illustration on the web. So if you have a neutron star, energy scales mega electron volt. And if we have in our atom trap the ultra-cold Fermi gas, we have a pico electron volt energy scale. But many, many elements of the physics, like superfluidity in Fermi gases or in the crust of the neutron star, are one and the same. So the same physics rules systems which seem to be totally different. So one appears in the ultra-cold atom lab and the other one in space somewhere, and have a completely different size and so on. But the basic elements of physics means just you have a fermion system, And the fermions have two different states. Neutrons can have a spin up and a spin down state. For the lithium-6 atoms, it's two different Zeeman sublevels, and they can strongly interact via nearly resonant scattering. And then these systems behave very, very similar. And in a way, you learn something studying these systems. You can learn something about, for example, the equation of state in a neutron star. So that's very fascinating. Same physics in completely different system or wide energy scale, but at the end, it's just the physics of strongly interacting fermions. Okay, so next slide is again a question for you. In the ultra-cold world, if you do experiments with ultra-cold atoms, which species are available for fermion experiments? Okay, I will show a periodic table and you answer the question. Where do we find fermions? Useful for our cooling experiments.
Lithium-7?
Lithium-7 is a boson.
6, then it's 6.
It's lithium-6, exactly. So if you look in the alkalis, lithium has two stable isotopes, one fermionic, one bosonic. I come to an example then. This is very nice. And there's another one in the alkali series.
So potassium 40.
Potassium 40, exactly. Potassium 40 and lithium, the alkali. We know, I mean, lithium-6 has a natural abundance of about 6%. It's convenient. Potassium has something in the 10 to the minus 4 range. It's very, very weakly radioactive and decays. So there's not much potassium 40. So we usually work with enriched samples of this. It's a little bit less convenient than the lithium-6, but both can be nicely laser cooled, and the standard methods of laser cooling and trapping work very well. But there are more candidates. How about the next group? Yeah, these ones. Okay, if you don't know, I can tell you. There is strontium. Strontium has a nice isotope, fermionic isotope, strontium-87. And it's interesting because it has an electronic singlet S0 and S0 ground state, but this has hyperfine, this has a nuclear spin, and so the nuclear spin has a splitting, according to the nuclear spin. So it has 10 ground states, very weakly, extremely weakly magnetic, and it's also used, interesting, for some experiments on many body states. And then there's ytterbium, which is quite similar to a group 2 atom, 2 outer electrons. And there are even two stable fermionic isotopes useful for experiments, 171 and 173. But there are even more.
Erbium.
Erbium. And the other one we are working with?
Dysprosium.
Dysprosium. Okay, I show two other ones. There are some experiments on helium-3 metastable and also on chromium. There has a fermionic isotope. It's a bit difficult to do this. But I mean, the one you mentioned now, dysprosium and erbium 167 and dysprosium 161, they are very convenient, and they have even a special type of advantage I want to discuss a little bit later for the fermion cooling experiment. But these are 8 species so far people have brought into quantum degeneracy of the fermions. So the choice is a little bit less than the bosons that you have. In particular, these ones here, dysprosium, erbium, terbium, the lanthanides, and strontium have become quite popular now for experiments. Now, a little bit of history. The very, very first experiment on bringing fermions into quantum degeneracy, a group of Degenerate and Boulder, and they were working on the fermions. And actually, at that time, Debbie was really a pioneer in the field, and it was not so clear that fermions would be interesting. Actually, people were arguing fermions are quite boring because what you do with fermions, you fill for BEC, you have a macroscopic quantum state, which is certainly fascinating. But for fermions, you just fill up all your quantum states level by level, then there's the Fermi edge, and that's it. That was, for some people, the argument. But it turned out, fortunately, that this is not true, this argument. So therefore, we were focusing on the bosons, and very few groups were working on the fermions. And Degenerate was the first with Brian DeMarco, and they could demonstrate the effect of Fermi degeneracy. They have the temperature in units of the Fermi temperature, and then they see that there is some excess energy in the expanding cloud, which follows the Fermi statistics. At the time, a relatively small effect, not very big, but a nice experiment, and the only one before the millennium that showed Fermi degeneracy. Potassium 40. Lithium 6. Now we jump into the year 2001, and there were two experiments, one in the United States, the Hewlett group. So that's the one with the collapsing Bose-Einstein condensate of lithium 7. He then worked with mixtures, and a very similar experiment in France at the École Normale Supérieure with lithium 7 and lithium 6. Quite similar, the experiments. And what Randy showed in the experiment was he had a mixture, both species together. And if you have a relatively high temperature, you see that the clouds have both the same size. So the size is just determined by, actually the thermal energy. So the trap potential is the same for both species, and they just have the same temperature. That means the cloud has the same size. So the mass does not play a role here. Yeah? The little mass difference. This is just the thermal regime. But when they cool down, lithium cloud gets smaller and smaller and smaller. But the lithium 6 cloud in thermal equilibrium, so you can assume that its thermal equilibrium, stays large. And here it's a T over Tf, temperature in units of the Fermi temperature of 1 over 4 roughly. And what you see in this comparison, it's very fascinating. You very directly see in comparison, this is a bosonic cloud without the Fermi pressure, and this is the fermionic cloud where Fermi pressure acts and the system cannot get smaller than. At T equals 0, it has a certain size and you cannot get smaller. And you see the effect of Fermi pressure directly in the experiment. And then when you cool further down the lithium 7, actually what happens in this experiment, the condensate collapses. You don't see it. Whereas in the Paris experiment, the difference was they were choosing different conditions, and they saw that lithium 7 also can condense. You have a BEC on top of the thermal cloud, and here the degenerate Fermi gas of lithium 6 together. But I find it very fascinating. What is the difference between the lithium 6 and the lithium 7 atom? It's just one neutron. The neutron is somewhere in the nucleus, and the nucleus is very small. It's more than 1,000 times smaller than the atom itself, or even more, 10,000 times smaller. And now the only difference is here, particles have one nucleon more. And this finds manifestation in a macroscopic behavior. The whole cloud behaves differently. I find this totally fascinating. Just a small, tiny neutron in each nucleus, and the system behaves macroscopically completely different. Fascinating. Good. Then a little bit more history. 3 other groups produced degenerate Fermi systems, potassium 40 in Florence, lithium 6 and lithium at Duke University in the United States, and at MIT. MIT, that's Kettler group, that's the Thomas group, and that was the Gusho group. And then now group number 7 with degenerate fermions, that was our group in Innsbruck in 2003. We produced degenerate fermions of lithium 6, being only number 7, but being the first group which were demonstrating a molecular Bose-Einstein condensation effect. So in this case, the particles pair up, and the lithium 6 molecules form dimers, and these dimers form a condensate, which could show here in this bimodal distribution. This is a partially condensed lithium 6 cloud, molecular cloud, and this is a fully condensed cloud. That was the first molecular BEC. Actually, at the same time as Degenerate, they produced also molecular BEC of potassium 40. That's a bit of history, and since then I've been always fascinated by the physics of fermions, and I think there are still many, many interesting things one can do with new systems. Yeah, and now some very basics of Fermi gases. In the trap, we have heard about several things already, which I will just repeat in this talk. of course, we have let's consider a box with the quantum states of the box. And then, you know, from this guy here, Wolfgang Pauli, and his principle that you can put one particle in one quantum state. That means if you have a T equals 0 system, 0 temperature system, you fill up state by state up to a certain point, and these are the occupied quantum states. Yeah, and the maximum energy here that is filled, we call the Fermi energy, named after Enrico Fermi. F stands for Fermi. Good. Now, the approximation that we usually make is that we have a relatively large system, so the quantum states are closely spaced and there are many of them, and so we consider them as a continuum. We do the continuum approximation, and we can write down an equation, not an equation, a density of state function, which for box potential is proportional to the square root of the energy. For harmonic potential is proportional to the square of the energy. And then we again have the occupied quantum states unresolved now, the continuum approximation up to the Fermi energy level. Okay, what next? Next, the Fermi energy. Now, if I integrate over the density of states and use the Fermi distribution, which fills all the states up to a certain Fermi energy, I can establish a relation between Fermi energy and the number density. And it's important that the Fermi energy, which is the relevant energy scale for a Fermi gas, is proportional to the number density to the power of 2/3. It's not proportional to the number density, it's proportional then to the number density to 2/3. In a Bose-Einstein condensate, so the local energy, which corresponds to the Fermi energy, the local chemical potential is proportional to n. Here we are proportional to n to the power of 2/3. That's an important difference. Now I can define a Fermi momentum. So P squared over 2m is the energy, and the momentum I write as h bar times kf, where kf is a Fermi wave number, the modulus of a wave vector. It's also a quantity which is often used. Why? Because 1 over kf, if you now consider this expression and rewrite it, we can show that 1 over kf, 1 over the Fermi wave number, is related to the number density to the power of -1/3, which is just an estimate for the typical spacing between two particles. Typical distance between two particles and the Fermi gas is given by 1 over kf. So this is our relevant length scale. So it's nice that we have a relevant energy scale, the Fermi energy. We have a relative momentum scale, the PF is h bar times kf. And we have the kf as Fermi wave number, which is where the inverse 1 over kf is the typical length scale. So the Fermi degeneracy defines certain scales for energy, length, momentum, velocity also, and also the typical spacing. Okay, that's important to keep in mind. Good, what next? A view in the lab. This is one of our labs. This is the lab in the Ikoki Institute. This is a typical lab. I mean, many of you, or probably all of you, have seen such labs. Here are the lasers on the table for potassium and lithium cooling in this case. And here is the main table where we have the vacuum machine, which I will discuss in a little bit more detail, and the control desk and the people operating the experiment, former postdoc of mine and a former PhD student. The photo is not very new. It's about 10 years old, but the apparatus looks still quite similar, although there's now much more optics and much more things we can do with the experiment. Good, next one. Now we consider the Fermi gas in a trap. As I told you earlier on, we consider the Fermi gas, or the ultra-cold gases, very often in harmonic traps, because harmonic traps are relatively easy to realize, nearly harmonic traps. So this is a trapping potential. So we don't consider any anisotropy. It's just we consider it's isotropic. Doesn't make a real difference. And now I come to the definition of the Fermi energy in the global way. In the global way, I take the Fermi edge maximum energy, which is here filled, to the lowest energy state available in the system. And I call this global Fermi energy. And how the Fermi energy can be calculated from the particle number and the energy, vibrational energy quantum, I have shown in, I think, the first lecture on Bose-Einstein condensation as a little exercise. So this is a simple expression which defines an energy scale, a global energy scale for the whole trapped Fermi gas. And for this energy scale and the potential here that you have, you can calculate the size, which we call the Thomas Fermi radius. And this size is given by this expression here. And because of the Fermi pressure, as you have seen in the experiment by the Hewlett group, the lithium-6 is relatively large. So because of the Fermi pressure, it can be few 10 or even more than 100 micrometer in the experiment. But now I want to consider this situation locally at a certain position. Well, let's select the position somewhere here. And now I can say here at this position, I can define a local Fermi energy, which is just the difference from the band edge to the lowest energy available here in the trap. And this local Fermi energy is the global Fermi energy minus the trapping potential. So the local Fermi energy is just a position-dependent function which reflects somehow the inverse trapping potential. So it's maximum in the center and then drops to 0 at the Thomas Fermi radius. So that's the definition of the local Fermi energy. And why is this interesting? If the trap varies slowly, so if this is relatively wide, which is in the Fermi gas usually the case, then I can say the Fermi gas behaves locally as it was in a box, in a little kind of virtual box. There's no real box, but we can consider this harmonic potential to be constructed of many little boxes. And for such a box, I can assume that the equations I've derived for box potential are valid. So I can use the box potential equation to model the system. And this is a very common approximation in the field. It's a so-called local density approximation. The only thing that counts is the local density, and then I can use the equations before to calculate spatial profiles or other quantities locally. That's done very often. From this assumption, I can easily derive the profile of the trapped gas. I hope this is clear. This is an important point. If not, please ask. Haven't got a single question so far.
Sorry,
Yes,
I don't quite get it why we can't treat it like a box. We don't really have the walls on the sides, right? Or
yes, but you can consider it as being composed of many little boxes, and if the box is still large compared to the typical extension of the quantum states, these walls don't play a role. You can then kind of simply neglect the walls. I mean, certainly quantum states with a very large extension are not considered in this box approximation. But if the whole system is large enough, it is still a very good approximation.
okay, so the quantum states are much smaller than the total trap and also than the box,
Yes.
then, right?
Yeah, you neglect certain quantum states which have a wave function which extends over the whole system here. But these are usually in practical, under kind of conditions that we have, this is a very good approximation. It works very well.
Okay, thanks.
Local density approximation. It's very often you find it in the paper, and we have made it already, actually. I've just called it in a little different way. It's the same as we did with remember we dropped the kinetic energy term in the Gross-Pitayevsky equation. And this is basically the same, what I do here, only described in a little bit different ways. And we call it therefore Thomas Fermi approximation also for the fermions, and there comes the name Thomas Fermi radius. It's a Fermi gas and the Thomas Fermi approximation, which is usually a super good approximation, even much better than for the bosons because the cloud is much larger. Good. So you can apply the box, and this helps you to connect locally. So with the equations we had before, let's have a look here. All these things now are true for the local Fermi energy and the local density, local Fermi energy, all local quantities. Good. Now we can easily understand what is the profile of a zero temperature Fermi gas. Then you simply take this local Fermi energy, which is the global Fermi energy minus the potential, and you take this and you have to take it to the powers of 3½ because number density and Fermi energy is related by this exponent 3½. And here's just the global. This is the global, and this together is the local Fermi energy. And then you see that the Fermi gas has about this shape. It looks nearly like a parabola, but there's still this exponent 3½ which deviates a little bit from the inverted parabola. If we do the same with the Tempus Fermi BEC, it would be a perfect inverted parabola. Here, it deviates a little bit. You see it a little bit in the wings. Okay, that's the profile of a non-interacting Fermi gas, degenerate Fermi gas, in this local density approximation. Now, finite temperature. What is the effect of temperature? And this can get already quite complicated. I don't want to go through all the mathematics needed for this. But what temperature does is that the Fermi edge is smeared out. It gets soft. Okay? And here, I mean, the temperature tells you about the size of the region where it's smeared out. And you can compare it to the total global Fermi energy. This gives you your T over Tf. And if you now look at the profile, what is the effect of temperature? If the Fermi energy has, let's say, 10% of the Fermi temperature as temperature, then the effect is there are slight modifications in the wings. And the wings look a little bit different. There are thermal wings appearing. But the overall shape does change very little. And this makes thermometry of a Fermi gas is actually challenging. It's not a trivial task to determine really the low temperature of a Fermi gas in a very good way. And if you analyze profiles, you can do it. And here are two examples from our work in Innsbruck. This is an example from the erbium experiments, and this is an example from the dysprosium experiments. And you see we take an absorption image of the cloud, look at the Cullen density, and then we analyze the profile, line density profile. And what the erbium guys did, that's an experiment by the Fellaino group in 2014. First, you do a fit to the wings only, a wing fit, and this gives you the dashed line. So it shows you, okay, with what? With a Gaussian. You assume the outer part is thermal, so you might do a Gaussian fit, and you extrapolate it to the center of the cloud, and you see it deviates from the Gaussian. Okay, but you can do better. You can do a fit by a so-called polylog function. So the mathematics is a bit complicated if you, so to say, integrate over the Fermi-Dirac distribution, and with a certain density of state, you end up with a so-called polylogarithmic function. It's implemented in most of the mathematics software and so on, but it's not completely trivial to do it. But this is a polylog fit. And here it's the same for dysprosium, where we applied polylog fits right away to get the temperature. In this experiment, I think the erbium had about 0.2 T over Tf. The dysprosium was a bit colder, 0.1. I think they also now have 0.1. But then you really get a problem, because if you have lower temperatures, it's very hard to measure. Then you have only a few atoms in the wings participating and giving some signal related to the temperature. It's very hard. But there we can do actually other things. And we managed in one of the experiments to measure temperatures of something like 0.05 or 0.06 times T Fermi in a different way. So how could one do it better? I mean, how Fermi gas thermometry? You have any idea?
Maybe with the time of flight, when you let it expand.
Okay, sorry, these are all time of flight pictures. You have the same problem in situ and time of flight. that you only a very few atoms are affected by the finite temperature. That's the same problem. You have to use a thermometer. Can you imagine what one can use as a thermometer?
Maybe one can use like another species of atoms and then go with collisions or something.
Very good. You use another species, and it is better to have a heavy or light other species.
I guess light, because you use light atoms.
No, then you are already quite deeply degenerate with a light species. I mean, then your T over TF is even lower for the light species and makes it even more difficult to measure the temperature. If you use a heavy species, this works quite nicely. And we did it with in a lithium-6 experiment together with potassium-41. 41 potassium is a boson and it's heavy. And then actually you can, under the assumption, that's of course what you have to check, that the sample is thermalized, you can determine the condensate fraction of the bosons. From that condensate fraction, you get the temperature of the whole sample. And in this way, we could quite reliably measure temperatures on the range of 5% of the Fermi temperature. Okay, so thermometry of Fermi gases is something which is not trivial, yes?
How do you know that your measurement is actually true? When you,
Yeah, you have to do certain checks. You have to study the thermalization process. I mean, one assumption is they are in thermal equilibrium. And okay, there's some thermalization by elastic collisions. So you can assume you wait long and then it will thermalize. But it is also not true, because if one species experiences some heating, you have a balance of heating and cooling. And so you have to check that you have the right cooling rate. You have to check heating in the system to justify these assumptions. So we did several additional measurements to support this claim that we are in thermal equilibrium. You can estimate, of course, you know the scattering properties. From that, you can already get an estimate for the thermalization times, but heating is still a problem. Good. So these are a few words about the Fermi gas thermometry. And now what else? How do we get there? But you know many of the ingredients already. And the first step is, like we discussed with other species, often Zeeman slowing, an oven. Here's the oven. Then you have some section where you can apply transverse cooling. You have a Zeeman slower section. This is the Iquoqui lithium potassium machine. And then you have the main cooling chamber. And we have discussed all the tricks already during the lecture. And in some cases, some species offer relatively narrow cooling lines. Like in strontium, ytterbium, dysprosium, erbium, we have convenient narrow cooling lines where simple narrow line Doppler cooling does the job already, the laser cooling job. So it's even better than any polarization gradient cooling and so on. So this narrow line cooling helps quite a lot. Good. So evaporative cooling I have discussed. You know how this works. I mean, just reducing the trap potential, throwing out the energetic atoms slowly enough so the cloud stays near thermal equilibrium, and then you get much colder. But now comes a very important point. For evaporative cooling, you need elastic collisions. And there are three ways to get them. We want to have S-wave collisions between unlike atoms. You know, fermions scatter, the identical fermions don't scatter in S waves. They scatter in higher partial and P waves and higher partial waves. So one option is the so-called sympathetic cooling. You use another species as a cooling agent, and you mix the other species with the fermions, and you hope you have good elastic collisions between the species and little collisional losses. And this has been used in the experiment of Randy Hewlett. I showed you the slide, the graph of the lithium-6 cloud together with lithium-7 cloud. This has been used by the Kettler group, cooling lithium-6 by sodium, or by Degenerate group with cooling potassium-40 by rubidium-87. And you find many other experiments using this so-called sympathetic cooling. It's just heat exchange with another species you can cool directly. Second option, you stay with unlike atoms, non-identical particles, you use a single species, but you use two different spin states. And this is done with lithium-6. It works very well in some experiments, also with potassium-40. It works with strontium-87 with many different spin states, with ytterbium and probably some other species. So collisions between non-identical atoms. It's important that that one atom is necessarily in a higher spin state. So this does not work if there are inelastic losses. But there is a third option now, which is relatively new. Yes?
How do you prepare the different spin states? So do you prepare them really, or is it just the fact that randomly you will have mixture of spin states?
It depends a little bit on the system. In many cases, if you start with a magneto-optical trap, you produce them already in the lowest two spin states. For lithium-6, if you operate a magneto-optical trap and you load the atoms from the magneto-optical trap into the dipole trap, you usually have some mixture of spin states. But it depends on little details of the loading process, whether you have a 50-50 mixture, 70-30 mixture, 30-70 mixture. So what we usually do is we apply a radio frequency transition and just mixing brutally the spin states. Just using a radio frequency mixing everything. In some experiments, you get after some cooling, you get a almost pure spin state, and then also you have to apply this radio frequency mixing. But it's not completely trivial, because if you just, for example, if you apply a so-called pi half pulse and you create a coherent superposition of a spin up and a spin down particle, then these particles, which are coherent superposition of spin states, are also identical. And you also can make them non-identical after some decoherence. And this happens automatically after a while in the trap because of different magnetic fields and so on. So an incoherent spin mixture you need. Good, but there is a third possibility, a third option, how you can cool the fermions. And this works even for some species in a single spin state. You know what I mean?
The dipolar scattering?
Yes, the dipolar scattering. And this is something which works very well for erbium and even better for dysprosium. In the dipolar system with strong magnetic dipole moments, you have a long-range interaction. So the potential drops r to the power of -3, not r to the -6. And this mixes then all the partial waves somehow. And even in the low energy limit, if you scatter at very low energy, the dipole-dipole interaction is relevant. And it has been shown theoretically that again, you end up with a constant cross-section. It's almost like S-wave scattering. At zero energy scattering, you have a constant cross-section, the dipolar scattering. And for dysprosium, this cross-section is as large as the one in rubidium-87 bosons. So the evaporative cooling works very well. And for example, we even have one experiment, dysprosium-potassium mixtures. I will say a few words about this, where the dysprosium is used as a cooling agent. Dysprosium atoms are cooled down and are used as a sympathetic cooling agent for potassium-40. So we do a similar thing like this one, but you don't use rubidium-87, we use dysprosium and rely on this dipolar scattering. Okay. So usually in textbooks you find, okay, at the ultra-cold energy limit, only S-wave collisions are relevant. This is not true. This is a remarkable exception for these dipolar collisions. Good. What makes fermions so interesting is another question which I want to answer. That's, if you look back a little bit in history, superconductivity and the standard explanation in terms of BCS theory in 1957. And the picture tells you that two fermions on the Fermi sphere with opposite momentum can somehow interact, and the interaction is in this case mediated by a lattice of a solid state, a crystal here. And so one electron distorts the lattice, and this distortion influences the other electron. This mediates an interaction. And the main thing is that this causes kind of a bound pair of particles with opposite momentum, which is called a Cooper pair. And these Cooper pairs can finally condense. They are bosons, and this leads then to superconductivity. And if you look into these superconductors, you find that the critical temperature for superconductivity is about 10 to the minus 4 of the Fermi temperature. Maybe in some high TC materials, it's a little bit higher. But 10 to the minus 4 is for us completely unrealistic to reach. We don't reach temperature, just 10 to the minus 4 of the Fermi temperature. We reach 0.1, but not much less, maybe a little bit less. But we have another advantage. We can compensate this with another one. What do I have in mind? We can manipulate the interaction. So we can make the system strongly interacting. How do we do that? Yeah. So just a repetition, which parameter characterizes the interaction in a quantum gas?
The scattering length?
Of course, the S-wave scattering length. Okay, we have to manipulate the S-wave scattering length. And then we have to distinguish between two different regimes. If the scattering length or the modulus of the scattering length stays small compared to 1 over kf, the inverse Fermi wave number, or you can write down the typical distance with particles in the Fermi gas. So scattering length small compared to distance, scattering length small, distance large between the particles. Then they sometimes collide. There are elastic collisions, and there may be some mean field. And this is what we can describe in a relatively straightforward theory with a mean field approach. Easy description. But if the scattering gets so large that it approaches the difference, or the distance between particles, then we no longer have a system which we can easily describe by some collisions or some mean field. This is what we call a strongly interacting system. And this is really exciting many-body physics, which challenges our theoretical understanding. This is really something really exciting. And we want to understand these strongly interacting many-body systems. So we have to distinguish these regimes, weak interaction, strong interaction. How we can control this, and this is what you all know now, I think, end of last lecture. I've told a little bit about Freshwater resonances. Here's again an illustration, which comes from the molecular potential, which we call the scattering potential with an entrance channel. And this couples to a closed channel, another molecular state, can couple resonantly to a bound state. And this can cause a scattering resonance. And then the scattering length typically looks like this. At a certain magnetic field, which we call B0, it diverges the scattering length. Normally below it is positive scattering length, and above it's negative scattering length. And then what is also important is that at large positive scattering length, you have a molecular state, which is very weakly bound. And in a certain range, it's universal. You can simply calculate the binding energy from the scattering length in a very simple way by 1 over by h bar over ma squared. That's a universal molecular state. So always a molecular state underlies the Freshwater resonance, and on the side where you have positive scattering length, you have a molecular state. Okay, so the detailed parameters, these can vary very strongly for different Freshwater resonances. But for us, it's the knob how we can control the interaction. Good, what else? Now we consider a spin mixture of two fermions with the Freshwater resonance. So let's say this is lithium-6 or potassium-40, and we have two different spin states here marked by the color, red and so these yellow or orange ones. These are the two different spin states, and they can interact. When red one cannot interact with the red one, yellow one not with the yellow one, but the different ones can interact. These are systems which are widely used And nature has made a remarkable gift to us. In lithium-6, there is a fantastic Freshwater resonance at a field of 834 Gauss centered, super wide, several hundred Gauss wide, and it's now very accurately characterized. And just by changing the magnetic field here, you can very accurately control the scattering length. And therefore, the lithium-6 system has been used as for many, now we could even say precision measurements of many body effects in such strongly interacting fermion systems. Potassium-40 works not as well as some, you cannot tune it as precisely, and it has some other problem, a little bit more losses. And now speaking about losses, our enemy, and also what it what makes the fermions different from the bosons, apart from the quantum statistics, the pure quantum statistics. I have mentioned three-body recombination. Three-body recombination in general means three particles come together in a three-body collision, and then two of them can form a dimer, a bound two-body object, and the energy released, the binding energy released, is then put into both the dimer and the free atom. So there's a large energy release which corresponds to the binding energy, and if it's happen, it's boom, then they simply explode out of the trap. So the energy release is relatively large, so normally they escape from the trap. And if this happens, we lose the atoms. Okay. In the case of a bosonic system, it can be a super strong effect. Within a millisecond, you can use most part of the atoms if you are on a Freshwater resonance. So a Freshwater resonance makes for the bosons, these losses bad, very fast. And one can show it scales with the scattering length to the fourth power, the loss rate of bosons. But for the fermions, there's a different story. For the fermions, remember, famous Austrian physicist, Wolfgang Pauli, for fermions, Pauli can suppress it. And how does it work? What is the idea? I cannot give really details, but the basic idea is if three particles come together close enough to form such a dimer, then you have three identical particles, or at least two of them are identical. Maybe even in a mixture. In a mixture, you have in a three-body collision, two from one sort and one from the other sort. And if they approach each other, Pauli's exclusion principle will work, and Pauli will not allow that they approach each other so closely enough, and will suppress this effect. Well, it's a Pauli suppression effect, so the three-body recombination can be strongly, by orders of magnitude, suppressed in a strongly interacting fermion system. And this makes the lithium-6 system on the resonance super stable. It lives many seconds or even longer. It does not decay in milliseconds, it lives seconds or even longer. Therefore, the suppression effect is very important. For potassium-40, it's a little bit less pronounced, and but it's in general a very important ingredient, which has been pointed out by this paper now quite some time ago, where they realized what the point is, why the fermions can live much longer than bosons on resonance. But that's cool. And we want to create strongly interacting many-body systems, and we know that this Pauli suppression effect helps us to make them stable. And this leads to several interesting applications. And let me look on these resonance again. This is the lithium-6 resonance for illustrative purposes. What are the different interaction regimes? If we are here on the right-hand side, so large negative scattering length, we have the attractive interaction, and this is a regime where pairing can happen similar to the BCS regime. So the BCS regime kind of works to a good approximation in this regime. Okay, if we go on the other side, oops, I told you positive scattering length means the system is repulsive. So the system would be strongly repulsive, and the strongly repulsive system would maybe phase separate, but this repulsive Thermigas is not the ground state. Remember, there's a molecular state below it. What happens is the ground state is a weakly bound molecular state. So if the system is here, the atoms will populate this super weakly bound molecular state and form these dimers, bosons. So here I have Cooper pairs, here I have bosons. And what happens here if I cross the resonance? Looks that the physics changes completely, but this is actually not true. There is a smooth crossover. The pairs are kind of molecules, weakly bound dimers, which are small compared to the interparticle distance. Now I approach the resonance, the dimers grow and they get bigger, 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 start to overlap and start to connect to Cooper pairs. And this is a very smooth behavior. The system, not as the pole of the resonance suggests, it shows no discontinuity. There's no phase transition, no nothing. And we call it a crossover. And this is famous as the so-called BEC, Bose-Einstein condensation, Badin-Kufer-Schreiber type crossover. Bcbcs, or sometimes most people call it BCS, BEC crossover. And this has been very widely investigated with the lithium-6 system. Then we ask ourselves, what happens exactly on resonance? What kind of state is it? Is it a bosonic state? Is it a fermionic state? The answer is kind of both. It has bosonic and fermionic degrees of freedoms. It's an interesting many-body state which has both bosonic and fermionic character somehow. But this is the so-called resonanced Fermi gas. Some people call it unitary Fermi gas. It's in the Fermi gas on resonance where the scattering length is super large, it diverges, and actually plays no more role because it's just infinity. Good. Now let's look at some of the funny properties of these unitary resonant Fermi gas. We consider T equals 0 Fermi gas a spin mixture of two different fermions. They are in the trap, and if there's no interaction, they just fill up the trap until you reach the Fermi level corresponding to the chemical potential here at T equals 0. Now I'm going to consider the same situation, 50-50 spin mixture, but now I switch the scattering length on resonance. I make it infinitely large. What happens? What do you think? Questions, what happens for A to infinity on the resonance pole? Will the system explode or what will happen? No idea?
If it's minus infinity, then we have infinite attraction. But the other way, we also have the Fermi pressure, which keeps the cloud. So we'll have something stable, I guess. And if it's for A equal plus infinity, then it will explode.
Okay, you are right. I mean, you get something, you get some kind of attraction, and the Fermi pressure counteracts. Plus and minus infinity is the same on the pole of the resonance. It's always, turns out it's always attractive, and but it's stabilized by the Fermi pressure. And what you get is a very similar situation. You get the same situation, but the chemical potential shrinks. It's filled to a new chemical potential, which is the old non-interacting chemical potential times a number. And this number is now called commonly in the literature Xi, or sometimes it's called the Birch parameter, because Birch is a nuclear physicist from the United States, and he formulated such a problem for neutrons, for strongly interacting neutrons. It's the Birch parameter, and this is a single number. And then you ask yourself, does this number depend on something? No, it cannot depend on something because there is no quantity it could depend on. It's just a problem of fermions, resonance scattering, and there's no other length scale I could compare it with. So this is a universal number, and this to measure it or determine it or calculate it theoretically has been a big challenge. Now I'm in experiments, and also theory have kind of converged to a value. It's known now within, I think almost 3 digits. And actually, a way to measure it is if you put it now into a harmonic trap, the effect of the attraction is the whole cloud shrinks, no interaction, an interaction shrinks, and then you can show that the size of the cloud, of the resonant cloud, is the size of the original cloud times this factor, the 4th root of Xi. And so early experiments tried to just detect the change in size of the cloud and derive this Xi parameter. And actually also we did it. So in harmonically trapped, these gases again rescale, shrinks in size, and keeps its shape. And in Innsbruck, we determined one of the early values, 0.32, with a very large error. MIT now, the best value, which is now on the market, is a measurement from MIT, which is this number here. And this turns out to be in agreement with very advanced many-body theory on this Birch parameter. So there was a lot of discussion and a lot of work just to get this single parameter right, which is highly non-trivial. Okay, so this is the resonant Fermi gas. Now coming to some early experiments, now promoting our own work a little bit. So we had such a system in 2003, 2004, lithium-6 resonance system. And this is the first observation of a molecular Bose-Einstein condensate, where you see here the condensate on top of a thermal cloud, a pure condensate. And then we converted the condensate by changing the scattering length. So we ramped up the magnetic field and went from the BEC regime to somewhere in the BCS regime. This in the center. At that time, I thought the resonance is there, but now we know it's a little bit lower. And we see there's almost no change. It gets a little bit wider. And this tells you that nothing dramatic happens in the crossover. It's just a smooth behavior. It just gets a little bit bigger. And if you get very high up, then you get a degenerate Fermi gas, and it smoothly connects to the Bose condensate of molecules. Here's an experiment where we excited the cloud macroscopically, shaking it, compressing it, and let it oscillate, looking at the oscillations. You can say that you measure compressibility in this way. And then we saw a funny behavior that there was a lower frequency below the resonance, the BEC regime. And then abruptly, somewhere in the BCS regime, it jumped to a value which was 2 times the trap frequency. This you can explain that they are no longer strong interaction. It's collisionless limit. They move as if they would not collide in the trap. But why is it so sharp here? And we now know that this is an effect that the system is superfluid up to this point, and then the superfluid behavior breaks down, and you break the superfluid by shaking the cloud. And here we have some non-superfluid way. Quantitatively, we had some discrepancy. This was for the unitary resonant gas, the predicted value, which you get by simple scaling arguments. And our measured one was below. But we learned that that was an artifact in the trapping potential. We had some ellipticity in the trapping potential, which explains this. So later we did much more precise measurements on this. Yeah, and then another experiment, this is excitation by radio frequency spectroscopy. And you see this is the radio frequency spectrum of a very cold cloud and a hot cloud. And you see kind of a bimodal behavior. And this signals what is known in superconductivity as the pairing gap, which is some binding energy of Cooper pairs, which we could see in this experiment. Okay, now coming to the topic of superfluidity. These were already early hints on superfluidity, but not a proof of superfluidity, I would say. But then, I mean, 2 experiments here. This is from the Degenerate group. And what they showed that they produced a degenerate fermionic system and could rapidly convert this into a molecular Bose-Einstein condensate by sweeping rapidly over the resonance. They could convert the Cooper pairs into molecules, and the molecules you see as a narrow peak in the expansion profile of the cloud. That's the observation of a fermionic condensate. And in 1 year later, the Catalan group, they looked at the rotating lithium-6 cloud, superfluid cloud, and then they observed vortices, a vortex lattice even. And this shows that there's a macroscopic phase coherence. A rotating system will show these vortices. And whenever you go around such a vortex, the phase advance, so to say, the phase integral is 2 pi over the vortices. And the vortices effectively repel each other, can crystallize and form a lattice. And that's a very clear signature of superfluid behavior. But superfluidity has been investigated in many experiments. For example, it's another experiment. Other features related to the superfluidity, that's the observation of a critical velocity. If you have the perturbation in your gas or in the Fermi system, which is slow, then there's no friction. That's superfluidity. But at a certain critical velocity, this breaks down, and the friction can, there's some friction with the environment, and this was done with some optical excitation, and they could show that there's critical velocity where there was no heating up to this point, full condensate fraction, and then there was some heating, and the condensate broke down. Observation of a critical velocity, also an important feature in superfluid systems. Here it's something which is a bit subtle, but which is also a clear hint on superfluidity or a clear observation. It's a quenching of the moment of inertia. What does it mean? Moment of inertia, so it's rotation, but it's a rotation without vortices. If you apply a slow rotation, then you don't create vortices. A smooth, gentle, slow rotation, you don't create vortices. But what in the superfluid part of the cloud cannot rotate, cannot carry angular momentum, only in the form of vortices. So if you prevent the system from nucleating vortices, the superfluid part cannot carry angular momentum. Only the thermal part can carry angular momentum. And there's a nice way to measure the angular momentum of such a cloud using basically the Coriolis effect. And we could do an experiment by slowly rotating a cloud and then seeing that at lower temperatures, that's here, that there's lower temperature, the cloud does not have the angular momentum of a rigid body. It's relative to a rigid body, it has less angular momentum. And that's a clear observation of the superfluid effect here. But then finally, another observation, another feature of superfluids is the so-called second sound. And you can have in a superfluid, you can have two different types of sound waves. One is a pressure wave, and the other one is an entropy wave. You call it a heat wave, but it's better to call it an entropy wave. And the speed of this entropy wave is much slower. So the upper one is the measured sound speed, the first sound speed, pressure wave, as a function of the temperature. And this follows theory. I don't want to go into details here. And we could detect another signal which was propagating much faster, much slower. And if you heat up the sample, it disappears. Here it's no longer superfluid. And then we analyzed this theoretically together with the Trento team, Stringari, Pitajewski, co-workers, and then we could show that it fits very nicely to the theory of second sound. So this was the first observation of second sound. And now many features of superfluid behavior have been observed in these Fermi gases. It's still an exciting topic. Okay, so in the rest of the talk, I want to introduce two experimental activities in our labs here in Innsbruck, both related to fermionic mixtures. One is related to mixtures of lithium-6 and potassium, fermionic potassium-40 and bosonic potassium-41. And the other experiment is related to Fermi-Fermi mixtures of dysprosium and potassium. But I just want to give you the basic ideas, not going too deep into the detail, just to give you a flavor of the research field. Good, so the first one here. Here's an illustration. You may wonder why I show this horse. So this is a real horse. This is a drawing from a textbook by Matuk, and this illustration is quite famous. This is a real horse. This is a real particle. Okay, now imagine that the real particle is a sand corn. Now that this horse, you assume it's galloping through a desert, and then it will be surrounded by a lot of sand. And then it moves as a horse surrounded by a cloud of sand, will move and will permanently lose sand corns, which will be kind of refilled by other sand corns. So it's permanently surrounded by a cloud of sand corns, but not the same sand corns. And it moves as an object which now is kind of shielded. It has a higher mass and what else? And also a finite lifetime, because the finite lifetime means that the cloud of sand is gone permanently being exchanged by other sand. And this is a nice illustration of what a quasi-particle is. In physics, we often consider, which is a powerful concept, we consider quasi-particles. And this is a particle, a real particle, surrounded or dressed by excitations, and the whole part of the object moves then together. Famous example, the very first example, is from the 1930s, work by Landau about the motion of an electron in a crystal, and the electron deforms the crystal, and if the electron moves through the crystal, the deformation will move with the electron. And this is a quasi-particle. But now we know many, many different quasi-particles, and in fermionic systems we have so-called Fermi liquids, where electrons or other fermions are surrounded by other fermions, and they move as together in form of quasi-particles. So it's a new particle with a different mass, a different energy, finite lifetime. That's our quasi-particle. And we are very much interested in quasi-particles, quasi-particle formation and Fermi gases. And so the illustration of the experimental situation we have in an optical dipole trap. So this is an infrared laser beam at 1064 nanometer usually. And here we trap a lithium-6 Fermi C, cloud of lithium-6 fermions, few times 10 to the 5 atoms, at temperature somewhere between 10 and 20% of the Fermi temperature. This is then prepared in a single spin state. So after cooling, we remove one spin state and it's just a non-interacting lithium-6 Fermi C. But this is doped now with other particles, so with potassium impurities. We have some, typically 10 or 20 times less potassium 40 atoms in it, and it can be potassium 40. On this slide, it's the fermionic potassium 40. It can also be the bosonic potassium 41. And we investigate now the behavior of these potassium impurities in the large Fermi C. And our ingredient is again that the interaction between the different species, between lithium and potassium, is tunable via a Freshwater resonance. We know these Freshwater resonances very, very well. Okay, so this is the Zeeman diagram of potassium 40. Because of the large nuclear spin, it has very many different sublevels in the ground state. But that's not so important. We work with two of them, which we just label by 2, second lowest spin state, and 3, third lowest spin state. I don't give all the other quantum numbers. Doesn't matter. Now the trick is that they have different interaction properties. While the lower spin state has just some background interaction, good for sympathetic cooling, but not for more. But the upper state has a Freshwater resonance. At a certain magnetic field, for the potassium 40, 154.7 Gauss, it has a Freshwater resonance about a Gauss wide. And so this state is resonant. If the potassium impurities are in this state, there's just some background interaction, essentially no interaction. Here, there is a tunable interaction. And now comes the main point, radio frequency spectroscopy. We apply a radio frequency to drive transitions between these two states, from non-interacting state to strongly interacting state, and we look at the spectrum then. Actually, we look at the number of atoms transferred from state 2 into state 3 in the experiments. And that's what we do for various interaction strengths. And here's the result, which is, here we tune across the Freshwater resonance. And this is a dimensionless interaction parameter, which contains the 1/kF and also the scattering length. So this is the usual way to express in a dimensionless way the interaction. Between plus and -1, this is strongly interacting. And then we see that the spectrum experiences an upshift in the repulsive regime, as we expect, and a downshift in the attractive regime. Then it becomes very complicated, and here it's a broad spectrum with a lot of mess here. I don't want to discuss this. I want to point mainly, okay, if you look at the spectra, they show interesting features. Let's look at this one. This typical spectrum shows a peak. We show this peak here in this color. And this is the and we see a background which is broad. The peak is narrow, more or less the Fourier will limited width of the excitation pulse. When the background is broad, it's on the order of the Fermi energy wide in energy. You see the same on the repulsive and attractive side. What does it mean? This is a clear signature of a quasi-particle. We call it a polaron for the fermions. It has a part in the wave function which contains the bare particle. This creates this narrow peak. And then there are a lot of excitations, and they create this broad pedestal. That's a typical polaron spectrum here that we see. Good. And now we were particularly interested in these repulsive, so-called repulsive polaron. This is a quasi-particle, which is repulsive, so as an upshift of the energy. And remember, below the Freshwater resonance on this side, there should be a molecular state. And when we started with this experiment, it was not clear whether this repulsive polaron would be stable enough or whether it would be rapidly decay into the molecular state. It decays, but slowly enough so that this quasi-particle exists quite close to resonance. This is the so-called repulsive polaron, which has been subject of many of our investigations now. And this is now a spectrum or result which is relatively old, 8 years or 9. But now we have slightly modified the system. Recently came back to the polaron research, and we work now with very similar system. The difference is that we work with potassium-41 impurities. They are bosons. And what can be different? Yeah, what is difference between bosons and fermions? The bosons can condense at the end. But if the system is not too cold, then we have only thermal impurities. And then we show that the spectrum here, upshifted and downshifted, is very similar to what you get with the fermions. So a thermal gas of bosonic impurities very close to the condensation point is very similar to the fermion gas before. But this changes when we get to lower temperatures and we form a Bose-Einstein condensate. And we see the difference. There's another branch. So this central branch comes from the Bose condensate. This is from the thermal particles, and this is from the Bose condensate. A new branch opens up in the spectrum, which much less energy shifts. So that is an important step to investigate density-dependent effect. So the polaron theory assumes that there's a single particle in the huge environment, in the huge bath. And the next step is to understand interactions. Now you put in more impurities and you ask yourself up to which point you can describe it as in this single impurity limit, or at which point do interactions set in. And that's really an open question. And this is now our main research challenge. We want to understand or observe interactions between impurities at high densities. And this Bose condensate has much higher densities, or it tells us that something dramatic happens. But there's a huge gap between this density of a condensate and the thermal cloud. We now carry out other experiments to understand what happens here. And now recent experiments, which were done with quite high precision, show some effects. We see that with the impurity concentration, the spectrum changes. And that's something we want to understand in more detail. Well, this is really a very open point. I mean, this theory of Landau's theory of Fermi liquid has two ingredients. One is the formation of polarons, and the second part is the interaction between polarons. And the second part is not really very well understood, and that's what we want to achieve in the experiments. Well, that was in a nutshell, very briefly, the idea of this experiment we are doing with the lithium-potassium mixtures. The second thing I want to tell you in a few minutes is what we are doing with dysprosium-potassium mixtures, fermions and fermions. Heavy one, light one, mass ratio is about 4. And yeah, we are interested in, can we tune the interactions? And can we create novel types of superfluids in these systems? What's the idea of novel superfluids? I mean, all the superfluidity we have seen in these Fermi gases, and which has been observed in many other systems, is kind of described by BCS theory or some extensions of BCS theory. But there are exotic cases where superfluidity can have completely different character. What I want to show here is a phase diagram of a Fermi gas, a two-component Fermi gas, with population imbalance. What does it mean? Population imbalance means that's the parameter P, polarization. If this is 0, you have a 50-50 mixture. If this is 1, you have 100% of one species or sort and 0 from the other one, and here it changes the role. And this is now what we call the polarization. Okay, what can happen here? And this is for a mass balance system, the lithium-6, let's call it a lithium-6 spin mixture. And then what happens is, and what has been confirmed experimentally, you get a superfluid phase, which is here. If you have equal populations, okay, you can get a superfluid, and if you are hot enough, the superfluid disappears here. Okay, if you, what does it mean here? This is the normal phase, which is non-superfluid phase. What does FR mean? FR means forbidden region. This is a situation which cannot exist, which is unstable. If you create a gas in that regime with a certain polarization and low enough the temperature, it will phase separate. The two components will repel each other and it will separate somehow. Actually, it separates into a paired fraction together with an unpaired fraction. This also has been studied experimentally. And TCP is a tricritical point. So this is where three phases can exist: the forbidden region, the superfluid, and the normal phase. But this is quite established, this kind of phase diagram. There's nothing exotic here. Maybe in a super small region, there might be some exotic superfluidity, which we cannot reach experimentally. But now we look into a similar phase diagram for a system which has different masses, a mass imbalance system, like lithium, potassium, mass ratio 6.7, or dysprosium, potassium, mass ratio 4. And then the phase diagram looks a little bit different, it looks distorted. And if you look at the right-hand side, it's very similar. You have a forbidden region, you have the superfluid range, you have a normal region. This is the side which is not so interesting. Very interesting now is the other side. Negative polarization in this diagram means there is a majority of heavy particles, so more dysprosium than potassium, let's say, in this example. And then there's something new happens. There's a so-called Lifshitz point, and there is where Cooper pairs become unstable. And below this, the Lifshitz point, what happens is theory predicts that there are now pairs of atoms existing with finite momentum. And that means for the wave function, you have a phase that varies in space. And this can be a kind of like a traveling wave or a standing wave. And these are then superfluids, which are called FFLO type. So Fulde-Ferrel-Lakinov-Shinnikov type, with this broken symmetry and spatially varying order parameters. And that's something very exotic. And there are very few experiments showing indications of it, not in our field. And with some organic superconductors, they have seen something like this. But this is for us now the main goal, the holy grail. Novel superfluids are expected. And the main point, if you look at the temperatures, this is in a range which is realistic in experiments. So it's realistic to get to these points experimentally. So it seems that the mass imbalanced fermion system, which is stable enough, has very good properties for studying new exotic phases of superfluidity. Okay, that's our holy grail. Let's go for it. That's the illustration of the holy grail. We need holy grails in the field, goals we want to achieve. So this motivates our work on these mass imbalanced Fermi systems, in particular dysprosium potassium. Just a few words. We started an experiment on dysprosium potassium back in 2013 with a completely empty lab. This is a photo of the vacuum machine in, I think, early 2017. Vacuum apparatus, main trapping apparatus, reservoir potassium, the dysprosium Zeeman slower. Now it's surrounded by a lot of optics. And this is done, the machine is running. And in 2018, we could demonstrate evaporative cooling of dysprosium and together with sympathetic cooling of potassium to degeneracy. Both are very cold. What is missing, or what was missing at that point, was resonant interactions. And so we conducted a search of Freshwater resonance, which takes a lot of time. I mean, you have to scan large ranges of a magnetic field and looking for resonances. But now we found one. I mean, in 2019, 2020, we found one. And actually, it has to be a broad one because only on these kind of resonances, the Pauli suppression works very well. But this is something we accomplished in 2019, 2020. And so we could demonstrate all key ingredients you need. And you can create a degenerate sample. Both species are degenerate. You have resonant interactions. And we also could demonstrate that the system is on a resonance rather stable. There's only very slow decay, which tells us the system is stable enough to look for new superfluid phases in this interaction regime. Okay, now we have been slowed down a little bit since last year because, I mean, not many people at the same time were admitted to the lab and all the complications. But we are in a very exciting stage now where we have shown that all the key ingredients for these novel superfluids work. And now we want to go for it. Okay, here's one result I want to discuss, which already signals that there are at least strong interactions. For the experiment, and this is the only experiment I want to show from this setup. So we prepare a mixture of about 20,000 dysprosium atoms and a few thousand potassium atoms together in a trap. And then we release them from the trap. They expand. And then we take, after 4.5 milliseconds, we take an image of both, of dysprosium and potassium. And here you see we are at a magnetic field of 235.4 Gauss. This doesn't tell you much, but this means at this field, the two species are almost not interacting. The scattering length between the species is very, very small. And so they expand both species freely. The dysprosium, the potassium. And potassium is by a factor of 4 lighter. And so the expansion velocity in the ballistic regime goes with the square root of the mass, so it expands 2 times faster. And there you see you have a denser potassium cloud, a smaller potassium cloud, dysprosium cloud, and a much larger potassium cloud. But this is what you would expect. I mean, 2 weakly interacting species, one heavy, one light, you would expect it. But the exciting point is now we do the same experiment, but on resonance, on top of a broad Freshwater resonance. Then you see that the picture changes completely. Here's dysprosium and here's potassium. And you see that the dysprosium cloud has about the same size as this one, but the potassium cloud is much, much smaller, almost the same size as the potassium cloud. So the interacting with potassium, with dysprosium during the expansion makes the potassium cloud to expand much more slowly. And this can only be a result of many, many collisions. And this tells us there's a hydrodynamic behavior. And this is a hallmark of strong interactions. So we see already that we can get to very large cross-sections for scattering. We see that we can enter hydrodynamic regime. The sample was not cold enough. This was around the Fermi temperature for dysprosium and for superfluids, but it's already quite interesting. And we saw by analyzing the cloud profile in more detail, even very funny things. It gets bimodal. It has a smaller inner core and a faster outer region. But if you model the expansion in detail with many collisions, we could exactly reproduce it. So we know what's going on, and we know that the system is resonantly interacting. That was a very important result. This, together with stability of the system, and makes it extremely interesting for future experiments. So we will have an exciting time with this experiment then. Now, okay, my conclusion is that ultra-cold fermions offer a great playground for physics of strongly interacting many-body systems, and many challenges are ahead for experiment and theory in the future. It's a very vibrant field with many things going on, particularly with new combinations. We enter new terrain. It's going to be very exciting. Okay, that's what I wanted to tell you about these systems. And finally, I've prepared 2 more slides, and these 2 more slides have questions for you. We see what you can answer. Okay, from this lecture, which atomic species are available for experiments with fermions? Name a few ones.
Well, we talked about erbium and dysprosium, for example.
Yes. And these are relatively new ones. The classical ones are
Lithium.
Lithium, potassium.
lithium and potassium. Then we have a few other ones, but we worked a little bit with strontium, but not with the other ones. Good. What is the profile of a trapped Fermi gas, I should say, at 0 temperature, at the 0 temperature Fermi gas? What determines this profile? What shape has it?
Not fully quadratic, but close to a parabola, but not.
Okay, close to a parabola, but with an additional exponent 3/2, yeah. Looks like an inverted parabola, but you have to take it to a power of 3/2. That comes from this Thomas Fermi approximation. How to cool fermions? What are the ways to cool fermions by evaporation?
Adding another species to have a thermalization, or using the same species but with different spin states, or finally dipolar.
Dipolar. 3 ways to do it. Yeah. What means strong interaction? How is strong interaction defined?
Having a large scattering length
Compared to what?
compared to the inverse K number.
Yes, which gives us what? Inverse K?
The characteristic length of the system.
The distance between the particles. Interparticle distance. Okay. How to control the interaction strength? That's what you certainly all know.
With Freshwater
The
Resonance.
Freshwater Resonance. Next slide. What is the Bcbcs crossover?
If you go over a Freshwater Resonance, that's that crossover when you go through that divergent section.
With what kind of species or combination?
What do you mean by that?
I mean, you just say you go across the resonance. That's true. But if I take a cesium bosonic system and I cross the resonance, I will lose them all.
With fermions.
With fermions in 2 spin states, yeah. Why is a resonant Fermi gas universal? Think about the length scales you have in the problem.
Maybe because the scattering length diverges.
Yes. And because of the divergence, I mean, its particular value becomes irrelevant. So it's just a maximum resonant Fermi gas, and the only length scale is your interparticle spacing or your 1/kf. If you have 2 length scales, scattering length and kf, it's important what the relation is between them. What is a Fermi Polaron?
Well, it's a fermion surrounded by excitations generated by like another species of fermions.
Yeah. Okay, in general, what the quantum statistics of the particle is not important. It can be a boson or a fermion surrounded by other fermions. So the important thing is that the medium consists of fermions. There are now also experiments on Bose-Polarons where people study impurities in boson in Bose-Einstein condensates. Okay, how can I observe superfluidity in a Fermi gas? Name some phenomena.
The vortices created by magnetic fields.
Okay, in this case, vortices is correct. So in our systems which are not charged, the vortices are created by simply steering the system. You take, for example, another laser beam as kind of a spoon, rotate the trap. Or you rotate the whole trap, you make the trap profile elliptic and let it rotate, and then the vortices appear. The magnetic field plays a different role in our experiments for tuning the interactions then. Another idea? One or two more phenomena?
You can also rotate it slowly, that there are no vortices, but like circular flow. I don't know if I can call it like that.
Yeah, then you have the so-called quenching of the moment of inertia effect. That has been used actually or as an argument for demonstrating the superfluidity of atomic nuclei. Okay, any other idea?
The second sound.
The second sound, yeah, that's another one. Okay, and I think there's the last question. What are new regimes of superfluidity? It's certainly a difficult one.
Yeah, in systems of great mass imbalance, when you have more of the heavy element, and you go like beyond the superfluid regime, but to the left where that SS regime is, so you have to be cold and you have to have a large imbalance. That would be that new regime.
Okay, well, that was my last question, but perhaps you have questions for me.
How does it come that you talk about like second sound? Like if it's enthalpy moving, where's the connection to sound? Like sound is a pressure wave. Why is it not like it could also be called second light? It's some kind of wave propagating through the medium.
Yes, it's a kind of more semantic question. What exactly you call sound? You have a definition which only considers a pressure wave, but anything which propagates, this other definition is everything which propagates through the medium in a wave-like matter is in a wave-like manner is what is called sound there.
How do you experimentally control exactly how much of a species do you have? So the proportion. How can you exactly say, well, I need half of dysprosium and the other half?
By changing, actually, that is not so super easy, but what we can change is the loading time of the species, the initial loading time, and transfer it. But it's mainly the loading time. Okay. Don't see any more question. And it's time to end this part of the lecture. I say goodbye. Ciao to all of you. I hope you have enjoyed it. Bye-bye.
Thanks. Bye.
Thank you. Bye.
Thank you. Thank you. Bye.
Thanks. Bye.